All right, looking at your homework from yesterday. Definition of derivatives. Calculating the derivative by definition. Typically, when you're trying to find values of the derivatives, that is not as challenging because it's easier to work with numbers in there. So when you go to the backside and you're dealing with values of the derivatives, that's not as difficult. It's when you're looking at your general derivatives on the front is where we start enjoying a little bit more. If we take a look at, do we have problems with number one, or were we able to make it through that? Okay. Number one, were you able to make it through? It's just dealing with your rational expressions. If we take a look at problem number three. Problem number three, we have h of x is equal to e to the x. And we want to find the general derivative to this in number three. Well, if we try to utilize the limit as t is approaching x of f of t minus f of x over t minus x, that doesn't get us anywhere. We run into problems. So looking at our second method of derivatives, limit as h approaches 0 of a difference quotient. So we have f of x plus h minus f of x. So we have e to the x plus h minus e to the x all over h. We still may sit there and say, yeah, that doesn't do anything for us. What does that do for us? Well, what it allows us to do is it allows us to use properties of exponents to be able to separate those two. Where if I know if I have x to the a times x to the b, and I want to combine these alike bases, what do we have to do with the exponents? Add them. So we have a plus b. Well, this property also goes into reverse. If I have two things that are two exponents that are being added, I can break them apart into the limit as h approaches 0 of e to the x times e to the h minus e to the x all over h. All we're doing is we're utilizing this property and going back in reverse. Okay, I have two things that are being added, I can separate them. Two exponents are being added, I can separate them. But now if we take a look, still doesn't really help us out too much. But if I look at what we have on top, I have a common factor between these two terms of e to the x. So we can factor out the c to the x. We can factor out the e to the x. So what we're left with is e to the x times the quantity of e to the h minus 1. Now what we need to do here is we need to take the limit as h is approaching 0. So doing a little bit more magic, black magic here, mathematical black magic, and pulling out my magic wand, Ali Kababa, Shishkumba, poof. We can write this. We can write this as e to the x times e to the h minus 1 all over h. So what I've done is I've sort of separated these two, and I just wrote this by itself. Well, using properties of limits, this is h is approaching 0. E to the x is going to be a constant, because all we are going to substitute in here is h for, or 0 for h. So my e to the x is just like a constant. So what we're able to do with this is bring the e to the x up front, because my goal when we're dealing with limits is put h or 0 in for h. Well, if I put 0 in for h still, I get e to the 0 minus 1 over value of 8 or over value of 0. Which still gives me 1 minus 1 over 0, 0 over 0. Really doesn't help us too much. But if we go to our calculator, and let's type in to our calculator, in our calculator, type into your y1 quantity e to the x minus 1 over x, or divided by x. Now I know this says h here. I get that says h, but we don't have an h in our calculator. So I have to do with what I have. So if you type in quantity e to the x minus 1 divided by x, and let's go back old school. Let's start putting in values that are getting closer to the value of 0. Let's put x, if x equals 0.1, x equals 0.01, x equals 0.001 as my values. What is y getting closer to? What is y getting closer to? And you can sort of see it on the graph because it will give you the graph there. Okay. Grayson, what's y getting closer to? 1. It's getting closer to 1. So this value right here, gets closer to a value of 1. So what we're left with is e to the x times the value of 1, or e to the x. So if I take the derivative of e to the x, I get e to the x. Sort of a nice derivative. And we'll utilize that as we go along. Students tend to like e to the x functions when taking derivatives, because the derivative of e to the x is just itself. Any other questions you have on derivatives, values of derivatives, definitions of derivatives? Once again, it's a lot of algebraic simplification. And once again, as I talked about before, it's a lot nicer when you have numbers there. Number 5 is a little tricky. That's the problem number 5. When you find your limit as x approaches 9, x plus square root of x minus 12 over x minus 9. And we have to factor this down. Really stretches your imagination in regards to factoring. But if I had x squared plus x minus 12, and I ask you to factor that, your two factors would be what, x plus 4 and x minus 3. And if I do my FOIL to undo this, I have x squared plus 4x minus 3x gives us plus 1x and a minus 12. I no longer have x squared plus x minus 12. I have x plus square root of x minus 12. I follow the same method of madness. What do I multiply by itself to get x? Square root of x. Square root of x and square root of x. If I multiply my FOIL, square root of x times square root of x, I get x. Combinations of 12, so I get a positive 1 here, would be plus 4 and minus 3. Now if I look at my middle multiplication, I have positive 4 square root of x minus 3 square root of x, gives me a positive 1 square root of x. On the bottom, I can factor that down once again to square root of x plus 3, square root of x minus 3. And so nicely these cancel out for us. So now I can put my 9 in there. So I have 3 plus 4, which is 7, and 3 plus 3, which is 6. So I have 7, 6. Once again, a little different flavor to your factoring. Something that you've never done before, but something that's very doable. Any other questions? Once again, derivatives will be a part of your mathematical life for the next decade now. Next 6 months, 4 months, 3 months. But dealing with the definition of limits, going through the definition of limits like we have here, is somewhat challenging at times. Okay? Somewhat challenging at times. So, of course, we're humans, and us being humans, we always look for the easy way out. So we look for some properties that will help us and assist us in dealing with derivatives. Now, you do not have to write this down except for the results. Okay? I'm not going to, because I'm going to go pretty quick through this. But the end is going to be the result, which is going to be the more important thing that we are going to look at. I want to find the general derivatives of all these functions here. Okay, let's just take a look at the derivative of x to begin with. So if I use my limit as t is approaching x of f of t, which is t minus f of x, which is x over t minus x. Well, I got t minus x and t minus x. They cancel, giving us a value of 1. So the derivative of x is a value of 1. Once again, key on the results. Don't worry about this right here. Take a look at the second one. Limit as t is approaching x of f of t, which is t squared minus x squared over t minus x. Factoring. This is the limit as t is approaching x of t plus x, t minus x over t minus x. Once again, the t minus x's, they move to Texas, leaving us with x plus x, which is 2x. So the derivative of x squared is 2x. Once again, don't sit there and try to run. I'm going to go very quick with these limits. Okay, those are pretty easy because those are easy factors. Now we start getting into a little bit more challenging factors. Limit t is approaching x of t cubed minus x cubed over t minus x. Okay, now we have to remember our difference of perfect cubes factoring, which is t minus x, t squared plus tx plus x squared over t minus x. Once again, the t minus x's, they move to Texas, leaving us with, substituting in our x, we have x squared plus x squared plus x squared, or if I put an x in there, I get x times x, which gives us x squared. So we have x squared plus x squared plus x squared, so we have 3x squared. limit as t is approaching x, t to the fourth minus x to the fourth over t minus x. Well, what we have is a difference of perfect squares on top. So we have a limit as t is approaching x, t squared minus x squared, t squared plus x squared over t minus x. The t squared minus x squared we can factor down still. So we have a limit as t is approaching x of t plus x, t minus, oopsie. Oh, here we go. T plus x, t minus x, and then we can factor this down, so we have t squared plus x squared over t minus x. Substituting x in for t. We have x plus x, and we have x squared plus x squared. So we have x plus x, which gives us 2x. We have x squared plus x squared, which gives us 2x squared. So we multiply them together, we get a value of 4x cubed. If we take a look at x to the sixth, we have the limit as t is approaching x of t to the sixth minus x to the sixth over t minus x. Well, this is the difference of perfect squares. It's also the difference of perfect cubes. Okay, I could use either one of them. Oh, let's see, what do I feel like today? We'll go to the difference of perfect squares to begin with. T is approaching x. X cubed. Let's see, how about t cubed? T cubed minus x cubed. Then we have a t cubed plus x cubed. And this is still over t minus x. Which we can now factor down as a difference of perfect cubes on top. We have a difference of perfect cubes, so we have t minus x t minus x. Then we have a t squared, a plus tx plus x squared. And I'm not going to worry about factoring that down because my goal is to get a t minus x there. Because I want to move them to Texas. So we have t squared plus x, or t cubed plus x cubed. Once again, my t minus x's, they move to Texas. Putting in x for t. So I have an x there, I have an x there, I have an x there. We have x squared plus x squared plus x squared. So we have 3x squared with the first term. And then I have an x cubed plus another x cubed. So I have 2x cubed there. So I have 3x squared times 2x cubed, which gives me 6x to the fifth. Once again, the key is the results. Because as we take a look now and recap a little bit, take the derivative of x, I get 1. Derivative of x squared, I get 2x. The derivative of x cubed, I get 3x squared. The derivative of x to the fourth, I get 4x cubed. The derivative of x to the sixth, I get 6x to the fifth. Using the pattern that we just formulated, if I was taking the derivative of 8, or x to the 8th power, x to the 8th power, what do you think the derivative of x to the 8th power is going to be, Todd?
8x to the 7th.
8x to the 7th. Now, how'd you get that? Well,
You move the exponent to the front and then minus 1.
there we go. We moved the exponent to the front and we subtracted 1. Exponent went to the front, we subtracted 1. exponent moved to the front, we subtracted 1. Well, what would happen, do you think, if I threw a coefficient there? Now, if I had 5x squared, what would happen? Well, let's now take a look at the limit as t is approaching x of 5t squared minus 5x squared over t minus x. Okay, this is what we've done. F of t minus f of x over t minus x. Well, the top, we could factor out the value of 5. So we have 5t squared minus x squared over t minus x. And then the t squared minus x squared, we could factor down again. Limit as t is approaching x of 5t plus x, t minus x over t minus x. And as always, our t minus x's have moved to Texas. So then I could substitute in my x for t. So we are left with 5 times 2x. Because x plus x gives us 2x. So I still, my x squared, following the Todd rule here, I can move my value of my exponent out front and drop my exponent by 1. So I had 2x, but I then had to multiply that by the value of 5, which is my coefficient, to give us 10x. So following the Todd rule here, and I want to find my derivative, I look at just my x cubed. If I was taking the derivative of x cubed, Sarah, what would that be? Just x cubed. 3x to the second. I'm going to take my exponent and move it out front, so I have 3x squared. And now I can just multiply that by the value of 7, which gives me 21x squared. Which leads us now to the exponent rule for derivatives. Whoop, whoop. Here we go. Life is good. If I'm in the form ax to the nth power, and it must be in this form, a times x to the nth power, and I want to find my derivative, I can find my derivative by taking my coefficient a. I can bring my exponent out front, so I have a times n, and then x to the n minus 1 power. So I multiply my exponent by my coefficient, draw my exponent by 1. Well, what if I had a constant? What if we had a constant? I want to take the derivative of constant. I want to take the derivative of 5. Well, there's no x there. But there is an x there. We can write this as c times x to the 0th power. Because we're saying there's no x's there, so I'm putting 0 there, because 0, the exponent, tells us how many times that base is used as a factor. Well, x is used as a factor 0 times. So I can write it 5 times, or c times x to the 0th power. Now, if I use the Todd rule here to find my derivative, I have c times 0 times x to the 0 minus 1 power. But that's c times 0. That's 0 using our multiplication property of 0, wipes everything out. So the derivative of a constant is a value of 0. The goal is to get it in this form, ax to the nth power. So if I have the derivative of a polynomial, I'm sorry, a polynomial function, and I want to find the derivative, we can find the derivative using the exponent rule of each individual term. So if I take the derivative of 4x cubed, Jenna, what would that be? 12x squared. I take my exponent, multiply it by my coefficient, and drop my exponent by 1. So I have 12x cubed. Then I can go to my next term, negative 5x squared. Take the derivative of negative 5x squared, Brandon, what do you get?
10x.
10x. 10x is the first. Okay, so I don't really need the first power there. My exponent of x is 1 here, negative 7x. Now I want to take the derivative of negative 7x. Jack, what do we get?
7.
Okay, minus 7. Because I'm going to get 7 times 1 times x to the 1 minus 1 power. I'm still following the Todd rule here. Okay, I'm taking the exponent here, taking the exponent and moving it out front. So I have 7 times 1. And then I'm dropping the exponent by 1. So I have 1 to the 1 x to the 1 minus 1 power, which is x to the 0th power, which means I don't need to write it then. Then I have a derivative of my constant, which we just said is going to be what? 0. So this goes to 0. So here's my derivative. No longer having to write the limit as t is approaching x of f of t minus f of x over t minus x. Could you imagine that? Or limit as h approaches 0 of f of x plus h minus f of x over h. Ouch. Okay, take the derivative of the next one here. What would be your derivative? Mike, what do you have?
Oh, wait, that one?
Yeah.
I wasn't making this little ones. 3, 5, x, 6, and then plus 11. Oh yeah, 22x, and 0.
Alright, so we're done with that. That's all we need to do. Plus our value 0, which we don't need there. Okay, what you will need to do is you'll see in the homework today, I'm going to give you first couple that you have to do the derivatives by definition. Okay, so you have to show that. But then you'll go to a section where you can find derivatives by either method. If you want to go back to definition, you can. If you want to utilize the rules that we're talking about today, you can. Oh, darn you, Mr. Gregory. Square root of x. Now what do we do?
Move the square root to an exponent.
Oh, what's the exponent?
1/2.
1/2. Ah, there we go. X to the 1/2 power. So I still follow my same methods of madness. My coefficient's a value of 1. So I multiply my exponent by my coefficient. And then I drop my exponent by 1. So now my exponent is what? Down? Negative 1/2. Now, I'm not going to ask you to rationalize solutions, but your solutions need to have no negative exponents and your radicals need to be simplified. So you need to have simplified radicals and you have no negative exponents. Well, we've just created a negative exponent. Negative exponent, where's it going to go then? We'll have a negative exponent. Well, I have to know my properties of exponents. This means they're reciprocated, so this is 1 over x to the 1/2 power. Negative exponent just sends it to the bottom, which now attaches it to the value of 2. So we have 1 over 2 square root of x. Let's again, need to put it back into radical form. Need to put it back in radical form. Not going to ask you to rationalize, but it needs to be back in simplified radical form. 8x to the negative, 8x to the 7th, 8 divided by x to the 7th power. Now, once again, we need to get in the form ax to the nth power for us to use that property. Well, how can I rewrite 8 divided by x to the 7th in the ax to the nth form?
You do 8 times 1 over x to the 7th.
Okay, so we have 8 times 1 over x to the 7th, but it's still not in that form. But how can I get in this a times x to the nth power? What can we do to move this back up to the top?
Negative 7.
There we go. So we have 8x to the negative 7th power. So now finding the derivative, we have our tag rule. See? You want to name something mathematically? We now have the tag rule. Okay, I multiply my exponent by my coefficient, and then subtract my exponent by 1. So Justin, what do we have? That's correct, because I have to multiply and then subtract 1 here. So I have negative 7 minus 1, which is negative 8. Negative 7 minus 1 is negative 8, not negative 6 that a couple of you wrote down and you had to erase. Well, once again, we need to put this into a no negative exponents, simplified radical form, which means I need to take this back down to the bottom. So we have negative 56 over x to the 8th power. Just go ahead and do this one here real quick. Check your answer, somebody around you. Todd, what do you come up with?
3 over x, or square root of
Yeah.
x. 3 over square root of x.
We have a square root of x, that's correct. We have 6 times 1/2 times x to the negative 1/2 power. 6 times 1/2 gives us 3. Negative exponent drops the bottom, square root of x. A normal line. We talk about a normal line. A normal line is a line drawn perpendicular to a tangent line at a point of tangency. A normal line is a line that is drawn perpendicular to a tangent line at the point of tangency. Okay, we've talked about tangent lines intersecting exactly one point or just touches. So here's your tangent line. Here's your tangent line. A normal line is perpendicular to the tangent line at this point of tangency. So we have our POT here. We have our point of tangency. And if we go perpendicular to that, this is a normal line. This is our normal line. Determine the equation of a line and tangent line and normal line at x equals 4. Okay, we have a function here. Now, what we've done up till now is we found slopes of the tangent lines is defined to us as limit as x approaches a of f of x minus f at a over x minus a. But as we talked about yesterday, this is also the value of your derivative at a. So to find our slope, we can first take a look at our derivative, which is a little bit easier to deal with. What's the derivative of x squared minus 7x plus 9? What would be your derivative of x squared minus 7x plus 9? Q? Use your exponent rule.
2x minus 7.
Minus 7. That's our derivative. To find the slope of our tangent line, I can find the value of my derivative at the value of 4, which is 2 times 4 minus 7, which is the value of 1. Oh, darn it. This is the slope of our tangent line. We can deal with our point of tangency. We have 4, let's see, it's 16 plus 9, 25 minus 28, negative 3. Or negative 3. But what I want to get to here is the normal line. We just found the slope of the tangent line. We want to find the slope perpendicular. What do we do to find our slope perpendicular? Opposite reciprocal. So we have 1 over negative 1, which is still negative 1. I need to get a better problem there. Show reciprocation. So first set of problems, you have to go by definition. Then from that point on, it is up to you what you want to do with respect to your derivatives. My suggestion is practice with the exponent rule. Just a suggestion. Solutions are posted. We'll spend a couple days on this. Have a good day.
Chris.